Hi everybody, welcome back. In this lesson we're going to be looking at limits at infinity and horizontal asymptotes. Now we're going to start off with the definition where we have the line y is equal to L is called a horizontal asymptote of the curve y is equal to x if either the limit as x approaches infinity for f of x is L, or if the limit as x approaches negative infinity for f of x is equal to L. Now you're going to see here that I have an example embedded here where we have a function f of x, and this is the first graphic. We have a function f of x, and we see that we have two different types of horizontal asymptotes. So that means that your function f of x or g of x, whatever function you're observing, can have two different types of horizontal asymptotes. And the function will strictly depend on what type of, the asymptotes will completely depend on what function you are observing or you are working with. In this particular instance, on the right-hand side of that graphic, I have that the limit as x is approaching infinity for f of x, this is equal to pi halves. And that's because as your x values get larger and larger and larger, meaning as your x values start approaching infinity, for this function f of x, this function f of x just kind of quote-unquote levels out to pi over 2. Now, as your x values get large in the negative direction, what's going to happen here is that the values for the function will again approach this horizontal asymptote, but this time they're going to approach a horizontal asymptote of negative pi halves. And so again, here we get to see that this function has two different horizontal asymptotes. And those horizontal asymptotes strictly depend on which x values are we approaching. Are we approaching positive infinity or negative infinity? Now, this topic of vertical asymptotes. So for horizontal asymptotes, we have that whole process to extract, but now we want to observe vertical asymptotes. For these vertical asymptotes, we want to determine where they occur at. And we want to make sure that these vertical asymptotes are not exactly holes on a graph, but more specifically that these are the vertical asymptotes that we want to observe. So anytime that we are testing for a vertical asymptote, we must approach the value in question from both the left and the right hand side. So on the right hand side of the graphic, well, first of all, you get to see that the graphic here does have a horizontal asymptote, and I'll get to that in a bit. But for the vertical asymptote here, the vertical asymptote of this graph is then going to be that as x is approaching 1 from the right hand side, the values produce negative infinity. As x is approaching 1 from the left hand side, so as we're approaching 1 from the left hand side, those outputs for the function start approaching infinity. In either case, we then extract that because we have one of the values from the left or the right hand sided limits approaching some sort of infinity, we have a vertical asymptote. And we're going to have a vertical asymptote here at x is equal to 1. So this is what the limits, as your limits are approaching a certain value from both left and right hand side, are evaluated at when you're given, when the evaluation is infinity or negative infinity. It implies that we have some sort of vertical asymptote. So again, we want to make sure those observations are the observations that we're making for this particular section. Now, once again, establishing that as x is approaching negative 3 from both the left hand side and the right hand side of that function, for negative 3, as we're approaching negative 3 from the right hand side, we get that x or that y values are unbounded towards infinity, and as x is approaching -3 from the left-hand side, then they're unbounded towards -infinity. This again implies that we have some vertical asymptote at x is equal to -3. Now, we did say that we have a horizontal asymptote, and we can identify that we have a horizontal asymptote for this function as x is approaching infinity for this function g of x. So g of x in this particular instance, as x gets large and large and large, we have that the y values for this function are collapsing down to 0. Similarly, the limit as x is approaching -infinity from this graph, we can see for this function that they're also approaching 0. This tells us that we have a horizontal asymptote of y is equal to 0. Now, you're also going to see on the graph that your graph g of x does in fact cross the horizontal asymptote. So your function can definitely cross horizontal asymptotes. However, your function cannot cross vertical asymptotes. And that is going to be something that we have to carry over and that we have to work with as we proceed through the course. So on the right-hand side, what we wrote out here for the vertical asymptotes and the horizontal asymptotes, this is a type of work that I am going to want to see as we proceed through the course when we're analyzing asymptotes or when we're analyzing end behavior for these graphs. We want, or I want, this calculus interpretation of what it means to be a horizontal asymptote and what it means to be a vertical asymptote. So not just relying on the definitions that we extracted when working with college algebra, but we also want to extract them in this type of calculus setting. So let's start putting this to work now. And let's see if we can keep on extracting the items that we're looking at. So for these examples, we're going to want to find the limit, or show that it does not exist. So for part A, we're going to be looking at the function, or the limit, as x is approaching infinity for the function square root of 4x squared plus 1, all divided by 2x minus 1. Now you might say, hey, what can we do here? Well, it's possible that we can go through and we can try to evaluate sort of a direct substitution. Now, if we go with a direct substitution, we're going to wind up with a limit for the numerator, which is going to be some sort of infinity, over the denominator, which is some sort of infinity. And therein lies the issue, that this type of evaluation will produce an indeterminate form. Now for us, an indeterminate form is not so great. However, this now tells us that we must use some sort of algebraic manipulation in order for us to be able to evaluate this limit. So the fact that we got an indeterminate form to start off with is actually really good. So what we're going to do now is we're going to start dipping into our algebra bag, and we're going to start trying to identify what can we do. Now, one option might be to rationalize the numerator, But in rationalizing the numerator, it's still not going to help us for what we need. Instead, let's see if we can find a workaround. All right, so I'm going to want to work around here, and let's see if we can find one. Square root of 4x squared plus 1 divided by 2x, whoops, divided by 2x minus 1. And let's see for this workaround. What I'm going to want to do at this point in time is I'm going to want to multiply both the numerator and the denominator. So both numerator and denominator, I'm going to want to multiply by some factor. Okay, so with this factor, I'm going to focus on the denominator. All right, so that's what I want to focus on first, is the denominator. And what I want to do with the denominator is I want to factor out a 1 over x. Now, if I'm factoring out a 1 over x from the denominator, then I must do the exact same thing for the numerator. Okay, so in this particular case, I'm talking about factoring, but we can also talk about distributing. Okay, so if I were to distribute this, what would those results be? And this is exactly what I'm looking at here. So as I'm working with this, and let me actually backtrack here. As I'm working with this, I'm going to have the limit as x is approaching infinity. Now let's distribute. My numerator is still going to be 1 over x. Multiplied by 4x squared plus 1 divided by, and this 1 over x is going to multiply that to x, which means we're going to be left with 2 minus 1 over x. So now the big question is, what do we do with that numerator? Well, for the numerator, we can then expand a little bit more. And the way that we're going to expand a little bit more for that numerator is going to be in this manner. That 1 over x can be reinterpreted as, and let me get a fraction bar going here. So the numerator, 1 over x, can be interpreted as the square root of 1 over x squared multiplied by 4x squared plus 1. Denominator is still 2 minus 1 over x. Now check out what happened with that numerator. That 1 over x is this exact same function here. So all I did was I manipulated that function for 1 over x in terms of its square root portion. And in this case now, because they both have the same square root, we can now distribute that square root and once we distribute that, we're then going to get a limit as x is approaching infinity for the square root of 4, because the x squareds are now going to cancel, plus 1 over x squared, all divided by 2 minus 1 over x. Now this is where we want to be. And the reason why we want to be here is because now as x starts approaching infinity, look at the look at the second term in that radicand. The second term in that radicand, the denominator is going to start getting really, really large as these x values approach infinity. In that instance, if the denominator gets very large, then the fraction 1 over x squared will start approaching 0. The fraction 1 over x, as x gets very large, once again, will start approaching 0. Therefore, the evaluation that takes place here is that as x goes towards infinity, we're then left with the square root of 4 over 2, which then turns out to be just 1. Awesome. And that's what we want to see. Now, in this particular case, this is where we decided to multiply by 1 over x, both numerator and denominator. And again, the reason we wanted to do that is because we looked at the denominator, which was 2x minus 1. We identified that the variable with the highest power was just the variable x. And that's why I then decided to multiply both numerator and denominator by 1 over x. Now, let's see what's going to happen for part B. So for part B, I'm going to have a very similar example to this. And this is going to be the limit as x is approaching negative infinity. And this is still going to be for the same function. 4x squared plus 1 divided by 2x minus 1. Now you might say, hey, Mr. Castro, this is going to produce the exact same result because it's the exact same function. And then I would say, is it? All right, so we're going to have to then go through the whole process. All right, we know that if we go through the whole substitution process, there's going to be an issue here. And the issue is going to be that we get an indeterminate form. So I just want to make sure that as we go through this, we're going to get infinity divided by, in this case, it's going to be negative infinity. Again, this is still indeterminate form. So indeterminate form for us is bad. However, there is a silver lining that we can use some algebraic manipulation to make sure that we extract the correct value. Now, what I'm going to do here to extract the value that we need, notice the indeterminate forms that are slightly different, however, they're still indeterminate forms. And they're slightly different in the sense that the denominator is approaching negative infinity for part B, and for part A, the denominator is approaching infinity. So slightly different variation, however, overall the exact same process. So let's keep going. For my numerator, I'm going to take a slightly different method here. And this is going to be my slightly different method. I'm not going to multiply by 1 over x. Okay, so let's make sure we change that. Instead, what I'm going to do is I'm going to factor out a certain variable. From the numerator, I'm going to factor out the variable of x squared. All right, so that's one of the variables that I want to keep in mind. All right, so factoring out the x squared numerator for my numerator, so the factor of x squared, I'm going to be left with 4 plus 1 over x squared, because again, once we redistribute, we're going to get that exact same value of 1. In the denominator, I'm going to keep it very similar, but I'm going to factor out an x value. So factoring out the x value will then give me 2 minus 1 over x as such. And we're going to continue with this process. So continuing with this process, the limit as x is approaching negative infinity, for my numerator, I now have the square root of x squared multiplied by 4 plus 1 over x squared, all divided by so that's all divided by x times 2 minus 1 over x. Now, this is looking pretty good so far, and I'm going to ask you to recall then. Look at this square root of square root of x squared. I'm going to write a big note right at the bottom here. the square root of x squared, this isn't just x, contrary to popular belief. It's not just x. This value is actually the absolute value of x, which means that the x value can take on two different forms. It can take on negative values and it can take on positive values. And this is rooted, that absolute value of x is rooted in a piecewise defined function, that we can be x, or let's say negative x, and this happens when x is less than 0, and you can say less than or equal to, and then it's going to be x when x is greater than 0. So again, we get a negative value and we get a positive value when we assume, or when we're looking at those respective domains. Now, using this concept, you're going to notice that the limit is approaching negative infinity, which means the domain that we're identifying here is going to be the negative value for that x. So when we take this limit as x is approaching negative infinity, we don't just get x for that numerator, we actually get negative x for that numerator. And again, that's all rooted in the sense of the square root of x squared is that absolute value function. All right, and so again, this is what we then get here. And notice that the x values are then going to cancel, and they're going to leave a negative 1. And then once we evaluate this, so the limit as x is approaching negative infinity, we get, let me come down here a little bit more, we get negative of the square root of 4 plus 1 over x squared to minus 1 over x, and then again, as we take the limit, that 1 over x squared goes to 0, and that 1 over x goes to 0, and we're then left with negative 1. And so again, we start seeing that this value isn't the exact same value that we got last time, but it's fairly close to it. And again, that's what we want to see. Perfect. So we can definitely see the different forms here, and those two different forms, or those two different values are the values that we wanted to see. So that's perfect for part B. Now we want to work with part C. So let's look at part C. For part C, we want the limit as x is approaching infinity for the function of x plus 3x squared divided by 4x minus 1. All right, and we're going to go through this process. All right, so as we're looking at this limit, we're going to see that we can take the exact same approach that we did in the previous section, in the previous examples. However, what you're going to notice is that since the denominator has a variable with the largest exponent just being 1, then what we can do is we can factor that variable as such. And when we do so, we can do the same thing for the numerator, where we're going to be able to factor out that specific value as well. So here for the denominator we get, for the denominator we get x times the quantity of 4 minus 1 over x. For the numerator, since I want the x's to cancel, I'm only going to factor out one of those x's, which means we're going to be left with x times the quantity of 1 plus 3x. And in doing so, again, we can see that the x's will then simplify, and the result will be 1 plus 3x divided by 4 minus 1 over x. And from here, when we take the limit as x proceeds to infinity, then the fraction in the denominator, this 1 over x, will tend to 0, and the numerator will then tend to infinity. So as we see here, we'll get some sort of infinity divided by 4, which in that sense would just tend to infinity. So when we're looking at this limit does not exist. However, this limit for this function is unbounded as x tends to infinity. Therefore, we can say that the limit as x tends to infinity for this function will then approach infinity. And that is what we, again, want to observe for these types of limits, is that sometimes they will exist, sometimes we'll be able to extract an actual limit value, and other times we won't be able to extract a limit value, which means we'll be looking at some sort of asymptote occurring as the x values tend to approach infinity or negative infinity. So let's look at one more type of example. On this example, we want to find the limit or show that it does not exist. And we're going to have two examples here. So part A, we're going to be looking at the limit as x is approaching infinity for x squared minus x to the fourth. Now, if x is tending to infinity in this particular instance, you can try a direct substitution. However, the direct substitution here, you're going to get that infinity is going to subtract infinity. And in that particular instance, when infinity subtracts infinity, we don't exactly get 0, because then we need to go through the whole analysis of figuring which infinity is going to be larger. So we can't directly make the substitution, or we can't do a direct interpretation for this function as x tends to infinity. So what we need to do is we need to algebraically manipulate this function so that we are able to then arrive at a correct interpretation for this function as x tends to infinity. That interpretation that we need, or that algebraic manipulation that we need, is factoring. If we factor an x squared component from both of the terms here, then we're left with x squared multiplied by 1 minus x squared. And a direct substitution at this point in time will then get us, for the first factor would be x squared. Well, then that would just be some sort of infinity, again, some very large number, multiplied by 1 minus infinity. And again, 1 minus infinity is just some very, very large negative quantity. So this can be interpreted as negative infinity. And so what we get here is a really, really large continuation of numbers multiplied by a very, very large negative continuation of numbers. Therefore, when we take the product of those two very large numbers and one of those numbers is negative, we then arrive at the conclusion that this limit will approach negative infinity. And so we then get to see here that the function will approach, or is unbounded, and it will approach negative infinity as your x values tend to infinity. So again, important concepts to see. And these important concepts happen when we're looking at them in terms of end behavior for these functions. Because again, we want to figure out, does this function have some sort of asymptote that I need to consider, or is it unbounded? And therefore I need to consider no vertical asymptote or horizontal asymptote. And for the very last example that we have here, we're going to take the limit as x is approaching infinity for the rational function of 7x to the fourth minus 5x squared plus 3x, all divided by 2x to the fourth plus 3x cubed minus 12. And again, we can take the exact same approach and identifying what is the variable with, looking at the denominator, what is the largest exponent on the variables? And as soon as we can answer that question, that is the exponent that we're going to factor out of each individual numerator and denominator. In doing so, we then arrive at the rational function for 7 minus 5 divided by x squared plus 3 divided by x cubed. All of this divided by 2 plus 3 divided by x minus 12x to the fourth. And as you notice, what I did was I factored x to the fourth from every individual term on the numerator and the denominator. Therefore, the x to the fourth will then simplify, and then we would be left with this function that we're looking at. Now, as the limit for x tending to infinity, then for every single fraction that we have, x is in the denominator, which means x is going to grow unbounded. Therefore, when we observe the fraction, in this case for 3 divided by x cubed, that fraction is going to get very, very small, and it's going to continue to get small as x tends to infinity. Therefore, this fraction will approach 0, and every single fraction that has a denominator of x will also be approaching 0. The result here would give us that we have a value of 7/2. So as your x values start approaching infinity or negative infinity, it's possible that your limit does exist, and if it does exist, then we need to find that numerical value for the limit. So I hope that you all enjoyed this lesson, and I will see you all for the next one. Have a great day.